Good afternoon, class. We are looking at Chapter 3 Derivatives. Here's Section 3.8 Differentials and Linear Approximation. We've covered the derivatives from derivatives and rates of change and its definition to derivative as a function, basic differentiation formulas, the product and quotient rules, the chain rule, the derivative of the log, and now differentials and linear approximation. Here's the synopsis of that, which we are going to go over in a moment. We've had a lot of differentiation formulas. Hopefully we all remember them so we can easily move on to applications. And as far as the log is concerned, if we can follow this arrow and get to this definition, in other words, going from logarithmic format to exponential format and vice versa, and noticing that log is simply an exponent. So log is y, the exponent of b to the power y. Then we can easily get these logarithmic properties that are pertaining to a general base b, and we can extend it to a common log when the base is 10. We can also extend it to natural log when the base is e. And I hope you see that from the general log to common log to natural log, ultimately it's understanding the concept of this arrow. The two functions are inverse functions, therefore they're symmetric with respect to the line y equals x. In general, logarithmic functions and exponential functions. In particular, we are looking at y equals e to the power of x and y equals ln x. We also have the change of base formula. Log x base b is log x over log b, or ln x over ln b. We looked at differentiation. The derivative of ln x is 1 over x. Ln of g of x is 1 over g of x times g prime of x. And if the base is anything other than b, we also tag along 1 over ln b. So if you look at this one, the derivative of log f of x base b is 1 over f of x. Flip it over. Times f prime of x by the chain rule, and 1 over ln b by the change of base formula. Now 3.8 differentials and linear approximation. The definition for y equals f of x, we define dx called the differential of x by dx equals dy, and dy called the differential of y by dy equals f prime of x dx. So I want you to pay attention to this graph, everybody. Notice we have a curve y equals f of x. We pick a couple of points, P and Q. P has coordinates x and f of x. For Q, we move to the right by some distance we're going to call that delta x, which is known as run. And delta x, also this distance of a BP or dx are identical. When we do that, along the curve, we create this distance, which is known as delta y. Along the tangent line, we create this distance is the dy. So along the x-axis, delta x and dx are identical. Along the y, it depends what you're looking at. So dy equals f prime of x dx, and here's the reason. F prime of x is dy over dx. If you treat this as a fraction, the product gives you, the proportion gives you cross product. dy is f prime of x dx. So this is how you calculate. Now, as far as understanding the graph, this distance delta y, or this distance bq, is cq minus bc or pd. So this distance rise along the curve bq is distance cq minus bc or PD or DP. And so delta y is this distance, or f of x plus delta x, minus this distance, or f of x, precisely. Clearly, delta y, this distance, is not the same as dy. However, we can replace delta y by dy for a function f, which is a continuous and differentiable function with a small delta x, if delta y is difficult to evaluate. For the sake of illustration, this has been blown out of the proportion, but normally delta x is extremely small, so dy and delta y are very close. Clearly, dy and delta y are not the same, as you can see here. However, when delta x gets smaller, dy and delta y get closer and closer, and that's the concept here. So f prime of x, which is dy dx, can be approximated by delta y delta x, and dy, which is f prime of x times delta x. Now we can approximate delta y by f prime of x times dx, or delta x. So delta y will approximate that, approximate delta y, which many times is easier to calculate. So in short, delta y is defined as f of x plus delta x minus f of x from the graph. If I move negative f of x to the right, becomes positive f of x, it gives rise to this equation, f of x plus delta x equals f of x plus delta y. We know f prime is dy dx, which means dy is f prime of x plus delta x, f prime of x times d of x. So over here, we came up with f of x plus delta x equals f of x plus delta y. So if I replace the delta y with dy in this formula, that gives us the approximation. We will look at examples of that later. If we call this point a comma f of a and find the equation of a tangent line at this point, it's known as a linearization. We know how to find this. We've done it many, many times before. What I want to show you is that the point slope says y minus y1 equals m times x minus x of 1. I move the minus y1 to the other side, becomes positive y1. I change the m to f prime of a, x of 1 to a, y sub 1 to f of a, and now we call this y L of x, which means the tangent line. L of x is f prime of a times x minus a plus f of a. Do I have to memorize that? Absolutely not. Just remember we use the point slope. Keep on doing the same thing to find the tangent line. What do we call that tangent line now? Linearization. So let's look at a simple example. Y, or f of x, is 4x cubed minus 3x. We want to find dy. So part A, simply put, differentiate, which is dy dx. And that means that 12x squared minus 3. How do you find dy? Same thing, times dx. Very simple, everybody. That's part A. Part B says, find both of them when x is 3 and dx or delta x is 0.2. First, let's find this one when we replace the x with 3 and dx or delta x with 0.2. Let's replace it. This is pretty simple. We can say this is 9 times 12 is 108 minus 3 is 105 times 0.2 becomes 21, because 2 times 105 is 210. You have one this. So as you can see, it's very easy to evaluate dy with the given numbers for x and delta x. Let's do the same thing for delta y. By definition, is f of x plus delta x minus f of x. Therefore, f of 3.2 minus f of 3. Elementary algebra, algebra, plug in 3.2, you get 4 times 3.2 cubed minus 3 times 3.2. Plug in 3, 4 times 3 squared minus 3 times 3. And put this into a calculator. This one is easy, of course, and you end up with 121.472 minus 99, or 22.472. Notice this was easier to evaluate, and that's why many times delta y is approximated by dy. One might say, okay, I think they are close. If you don't think they are close enough, take a look at the concept of delta x versus x. The smaller the value of delta x compared to x, the closer these two values. If you make it 0.1, they are closer. If you make it 0.01, they're almost identical. For y x times 4 minus x quantity cubed, find dy. So simply put, you have to differentiate this, so that uses a product rule. So you need f prime, which is 1, times g, which is 4 minus x quantity cubed. So plus g prime, the derivative of the second piece is 3 times 4 minus x squared times negative 1 by the chain rule, and then times x. In other words, we have f prime g plus g prime. To simplify, we take the 4 minus x out with the exponent 2 as a common factor, because 2 is smaller than 3. When you divide this one by this one, gives you 4 minus x. And this one, 4 minus x squared, goes away. The rest of it, positive 3, negative 1, and x gives us negative 3x. These two combine into negative 4x. Now you can leave it like that, but I'm going to take the negative 1 out because it's going to make the next step easier. When we take the negative 4 out, my apologies, we get x minus 1, and we rewrite it as such. So that's dy dx. But what is dy? The same thing, times dx. So dy is the same thing that we got here, minus 4 times 4 minus x quantity squared times x minus 1. Now tag along dx times dx. Now we want to find dy and delta y when x is 5 and dx or delta x is 0.1. So simply put, plug in. What do you plug in? X is 5, dx or delta x is 0.1. See how easily we can calculate this, everybody. This is negative 1. When you square it, becomes 1. Negative 4 times 1 doesn't change anything. It's negative 4. Times 3, negative 12, times 0.1, negative 1.2. It's a very easy calculation, as you can see, everybody. Delta y, by definition, is f of x plus delta x minus f of x. So it's f of 5.1 minus f of 5. Which means we are going to plug in 5.1 into the original function. So 5.1 times 4 minus 5.1 cubed, and then minus f of 5, which means we're going to put 5 times 4 minus 5 quantity cubed. And this one, you have to subtract 5.1 from 4, okay, negative 1.1, raise it to the power of 3 times 5.1, do the same thing here. This is negative 1 cubed times negative 5. When you do the math, you end up with negative 1.7881. And what I want you to notice, this is more difficult than calculating this. And that's the idea. This is more difficult when you compare. As far as the two values are concerned, the two are pretty close. And again, the smaller the delta x, the closer these two values will be.